So we've been looking at this idea of looking for association between two quantitative variables. And I started off by talking about you could put up a scatter plot, and one of the first things you could look for is just, is there any visible pattern to the data? And for us, we're just going to be looking at a linear pattern. Data could have other patterns, quadratic, polynomial, any kind of polynomial, trig function, exponential. But we're just going to focus on linear. And now what I want to talk about, I've referred to the idea of there's some ideal line, but we haven't really talked anything about that. So let's look. The idea is this data here. I've just made up some data here. We've got the explanatory on the x-axis, response on the y as typical. And what we're interested in is there's some line through here that is best at fitting that data. And what do we mean by best fitting to the data? Well, what we'll do is for any line, so imagine all possible lines that could be drawn, you could compute the distance here, just vertical distance. That one, there's barely any difference. We could tally up all these distances. And so we could look at those distances, and then we could say, well, which line would cause those distances to be the smallest? You can think of that distance as your error. Right? This is what actually was observed, and here is what the line says. And so each one of those little line segments is measuring an error. And we want to find the line that would minimize that error. Now, this is something that is accomplished through calculus. Calculus can find minimums and maximums of functions. And so there's a straightforward formulation for how you would do that with calculus. We will rely on the technology to give us the line, but I want us to understand what it is that line is minimizing. So each one of those distances is called a residual. In your mind, and in my mind, I always think of that as error. And it's computed by taking your observed y and because that comes from our sample, we often put a hat on it, just like we did for proportion. So we have some observed value, and then we've got the predicted, which is the y on that line. So each one of these is taking the observed minus the y value on the line. So any of these points that's below the line, the residual is going to be a negative value. And any of these points above the line, the residual is going to be a positive value because of the order of this subtraction. OK. And so let me fix that. I wrote that backwards. Y will be our observed. Y hat is our predicted. So the y hat is the y off the actual line there. And so we know from algebra what a linear equation looks like. The notation's a little bit different in statistics. But you have some A and B there that describes the line. So this equation predicts y values, hence the y hat. So for any given x, this line predicts a y value. Those are the y's on the line. And these are the actual y's from our data. So remember from algebra, the a there, the notation's a little different, but a is our y-intercept, and b is our slope. I know in algebra we usually use mx plus b, so b means something else in algebra, but the form is the same as what we're used to. OK. So what we're looking to minimize is not just the sum of these residuals, because some of them are positive, some of them are negative, and they would cancel each other out. What we'd really like is how far that is without a sign, so that it was always positive. So one approach would be to just take the absolute value of these residuals. And we've seen something like that in our MAD statistic. What we'll do is actually take the difference squared. So we are going to try and, this line here is trying to minimize the sum of the squared residuals. So because of that, this is sometimes called the least squares line, or least squares regression line. The squares being the squares of these residuals. So each one of these could be positive or negative, but once you square it, they're all going to be positive. Add up all those squares. And this particular line, the best fit is going to be the one that makes this a minimum. And it turns out from calculus, you can show that there is only one line. So there's not two different lines that'll give you the same minimum sum of the squared residuals there. So there is a unique line for every set of data that is the least squares residual line. So let's move on over to the app. We'll use that house data and square footage to show how you can get the applet to give you this least squares regression line. So I'm in the correlation regression applet, and I've already pasted in that square foot and price data. Use data, so here it is. And if you click on this box, you get a visual of that least squares regression line. You can even have it show you, just like I did, all the residuals. So there it's drawing in the residuals. And it's giving you the equation of that line. Now notice it's not using y and x. This is actually a little bit nicer for interpretation. It reminds you of what those variables represent. So here's the a, the intercept there, 265,222.12 cents. Here's the slope, 168.59. And then that's not an x there, that's times. The square foot is the variable, right? So you've got the x-axis variable is square feet. The y-axis variable is price. And they've tried to, in their sort of crude way, put the hat on top of that price, but it ends up after it there. So really, they're putting in the actual names of the variables in place of y and x there. So you can see those residuals to remind you of what those are. The squared residuals, I'm not sure visually if that is helpful, but the area of each one of those squares, when you square a residual, you just take that value times itself. It'd be the area of those squares. So one way to visualize what the least squares is doing is minimizing the sum of the areas of all those squares. But I like to just see those errors there. And then recall from before we were using this, you can look at the correlation coefficient. So and this here is just the sum of the absolute errors that they're giving us, just as an extra statistic. So remember I said you could take the absolute value of each one of these errors, and that's what they've done and added them all up. just as sort of a measure of how linear it is. One thing that's nice in this app is you can play around with your own line to try and see if you can do better. And here's my number. In the blue line that I'm playing around with, I've gotten it down to 884,233. I'm not less than that one. And you could try and find a better line, but you shouldn't ever be able to get a sum of your absolute errors to be less than this one, because this is the least possible error that you're going to get on the best fit line. So you can actually try even before, just to get some intuition. You could turn this off and just play around with that movable line till you felt like you'd minimized those errors as best you could, and then see how well you did compared to the actual best fit.